Okay, so this is Unit 5, Integrals Involving Inverse Trig Functions. Recall from our differentiation unit that the derivatives of the 6 inverse trig functions form 3 pairs, with each derivative in the pair being the negative of the other, as you can see from the arc sine to the arc cosine. We also found these derivatives using implicit differentiation, and you can go back to that video if you need to for a refresher. As such, when you're anti-differentiating, there's not going to be 6 formulas. Rather, we can get by with only 3. So convention says that we're going to use the positive forms of the antiderivatives, which means that there are not anti-differentiation formulas involving inverse cosine, inverse cotangent, and inverse cosecant. The derivation of the formulas that we find are best understood by differentiating the resultant antiderivative in each case. So if we begin with the derivative of arc sine of u over a with respect to x, we have d dx of arc sine u over a plus c. It's going to give us 1 over the square root of 1 minus, this will be u over a quantity squared. And again, because the u is a function of x, we're going to have du. Using some algebraic simplification, this becomes 1 over the square root of a squared minus u squared over a squared, and again, du. So further simplifying, we have 1 over the square root of a squared minus u squared, and since the square root of a squared is going to be a, du, and this will give us our final formula, a over the square root of a squared minus u squared du. So continuing with the integral of arctan, we're going to differentiate 1 over a times arctan of u over a plus c. We can see that the 1 over a will come outside because it is a constant. And we have 1 over 1 plus u over a quantity squared du. A little simplification, we have 1 over a times 1 over a squared plus u squared over a squared du, which gives us a squared, 1 over a on the outside, times a squared plus u squared du. Last simplification, we have a over a squared plus u squared du. Okay, looking at the arcsecant, we have d dx of 1 over a times the arcsecant of the absolute value of u over a plus c, which gives us 1 over a. This will be 1 over the square root of u over a in the absolute value times the square root of u over a quantity squared minus 1 du. So continuing the simplification, 1 over a, absolute value of u over a, square root, this becomes u squared minus a squared over a squared du. which is 1 over a times 1 over the absolute value of u over a. And this becomes the square root of u squared minus a squared over a. So we can bring the a up, and the a becomes a over a times 1 over the absolute value of u over a times the square root of u squared minus a squared. And again, du, which I left off up here. And the last simplification, we can bring this, and this becomes a over u times 1 over the square root of u squared minus a squared du. Now, the primary method of using these formulas is through pattern recognition, which only comes with practice and memorization. It is worth knowing that if an inverse trig integral does appear on the AP test, it will most likely be that of either inverse sine or inverse tangent. Inverse secant rarely happens. Okay, so let's do some practice problems here. So we have the antiderivative of 4 minus x squared. And we recognize this as the form of the integral of du over the square root of a squared minus u squared, which we recognize as arc sine. So we recognize that then u squared is equal to x squared, which means u is simply x. Du will be dx. We need a squared will be 4, which means a is just going to be 2. So then this gives us the antiderivative of arc sine of u over a plus c, which is then arc sine of x over 2 plus c. So looking at this next one, we recognize that there is no square root and there is a plus, so it's going to be an arctan. So let's look, and we can see that u is going to be, u squared will be 9x squared, which means u is going to be 3x. So du is 3dx. A squared is 2, which means a is going to be the square root of 2. Now, because we don't have a 3 in here, we know from our u substitution that we need to divide by the 3. So now we are in the form of 1/3, because that 1/3 gets factored out, of du over a squared plus u squared. This is going to be 1/3 times 1 over a arctan of u over a plus c. So substituting in everything, we have 1/3. This is 1 over square root of 2 arctan of 3x over the square root of 2 plus c. Okay, so let's take a look at this last one. We recognize that there is an x on the outside of the square root, which means we know that we are going to be in the form of du over u times the square root of u squared minus a squared. But there's going to be a couple of things that we need to do to manipulate this. So we start by recognizing that u squared is going to be 4x squared, which means u will be 2x, and du is 2dx. Now we need to recognize that we don't have, down here with this x, we don't have a 2, and we don't have a 2dx. Now we can put both of those in, unlike what we've done with u substitution previously. because then we're only multiplying this entire integral by a2. So this gives us then everything that we need. Now we recognize that we have a squared is going to be 9, so a is going to be 3. And I'm going to go ahead and put this 2 over 2 on the outside so that it does match. Now this becomes 1 over a, the arcsecant of the absolute value of u over a plus c. So plugging everything in, we have 1/3 arcsecant, the absolute value of 2x over 3 plus c. Now, unfortunately, as is typical of calculus, the straightforward application of these rules is not something we usually see. The integration formulas for inverse trig functions can be disguised in many ways. For example, in example 2, if we have the area of the region bound by f of x is 4 e to the x over 1 plus e to the 2x, the x and y axis, and x is equal to the natural log of 3. So we need to set this up as the integral from 0 to our upper bound of the natural log of 3 over 2 of this function, 4 e to the x over 1 plus e to the 2x dx. Now, right away, you should recognize this as an arctan because there's a plus and no square root. So just as we did above, let's go ahead and identify our u squared is going to be e to the 2x, which means our u is e to the x. Our du is e to the x. A squared will be 1, which means a is 1. Now, we do have the special case where we are going to change our limits of integration. So we have that u of 0 is going to be e to the 0, which is 1. And u of the natural log of 3 over 2 is going to be e to the natural log of 3 over 2, which is simply going to be the square root of 3. And if you need some help on that, look up your rules of exponents and natural logs. So now we have 4, because this 4 in the numerator factors out, times the integral from 1 to the square root of 3 of du over a squared plus u squared. So that gives us 4 times 1 over a of arctangent of u over a evaluated from 1 to the square root of 3. Now we need to go ahead and put in our a, which we recognize as 1, so this is very simple. So this then becomes 4 times the arctangent of u evaluated from 1 to the square root of 3. The arctangent, so we now have 4 times the arctangent of the square root of 3 minus the arctangent of 1. Arctangent of square root of 3 is going to be pi over 3, so we have 4 times pi over 3. Arctangent of 1 is pi over 4, so which gives us 4 times pi over 12, which gives us a final solution of pi over 3. Okay, so let's go ahead and look at example 2. So in this one, we need to separate this into 2 integrals. So we have the integral of x over the square root of 4 minus x squared dx plus the integral of 2 over the square root of 4 minus x squared dx. So I'd like you to go ahead and work. We're going to do one of these. The first one is going to be basic u substitution. So u would be 4 minus x squared. Du is negative 2x dx. So we go ahead and divide through by that negative 2. And we can rewrite that first integral as negative 1/2 the integral of 1 over the square root of u du. And this second one, u would be, this is an inverse trig, so u squared is x squared, which means u is going to be x. Du would be dx. A squared is 4, which means a is 2. And so we have plus 2 times the integral of du over the square root of a squared minus u squared. So go ahead and finish up that integral as one of your questions in the video. Okay, so we're going to go ahead and skip the next one, and we will do that one in class. So the last one we're going to do is the e to 1 over the square root of e to the 2x minus 1. So in this one, we recognize that it looks a lot like arcsecant. So let's go ahead and see what we can come up with. So we have u squared would be e to the 2x. So u is going to be e to the x, and du is e to the x dx. A squared is 1, and a is equal to 1. So the only thing that we're missing in order for this to be a arcsecant is we need the du needs to have an e to the x in the numerator, but we also need a u here. Well, because e to the x over e to the x is simply 1, we can rewrite this integral as e to the x dx over e to the x times the square root of e to the 2x minus 1. And now we have forced this into the inverse secant form of du over the absolute value of u, and we don't need the absolute value because e to the x is always positive, times the square root of u squared minus a squared, which gives us then 1 over a arcsecant, the absolute value of u over a, plus c. So substituting everything in, we have 1 over 1 arcsecant, absolute value of e to the x over 1 plus c. Simplify everything, arcsecant, and again we don't need the absolute value, plus c.